need to make 2 of these cam screws. These will be machined out of 42 chromoly 4, otherwise known as 4140. They get a 5mm hex on one end, rotary broached or wobble broached, and the center section here is offset by 0.45 millimeters. That's it, yeah. Normally you would do this on with a 4-jaw independent chuck or with an emergency collet that has been bored off center. I don't want to waste an emergency collet for 2 parts, and I don't have a 4-jaw independent chuck, so there is another way to do this. I got my stock here in the 6th jaw. I have it sticking out a little bit over 30 millimeters. That's what I need to turn the first side. Using a DC MT insert for stainless, which also happens to work very well for 4140 or 42 chromo 4 with commercial heat treat. To the first pass, take a quick dimensional check if my DRO is set right. I will turn the whole length down to 8 millimeters and leave some material on the area that's going to be the eccentricity. The end gets turned to 7 millimeters. The eccentricity is right in this area here that we left a little bit heavy, and we'll take a grooving insert, plunge in and move to the right side. But for that we need to clamp the part off center, and in this case it's very easy because this is an adjustable a buck style chuck. Can be moved on center, but in the same way as being moved off center, you can also put on center. It can also be moved off center, which I would not recommend to turn eccentricities with a very large throw, but in this case it's only 0.45 millimeters, and if we do not overdo it with the RPM, the machine will not jump off the table, so everything will be fine. Okay, got an indicator in place. We will set it to a convenient number like 0, and then we use the adjustment screw back here to pull the part off center, and we want 0.45 millimeter eccentricity. That's a total throw of 0.9 millimeters. So we just move the chuck over 0.45. There we go. This should give us, out traveled the indicator. Let's go to 0.9 and it should drop back to 0. There we go. 0.9. That's plenty accurate enough for this. This is just like on a cam lock chuck. It's a locking cam. It's that fast to set this chuck to do slight off-center operations. When it's done, now I can set the chuck back to 0. I'm just using a piece of an ejector pin clamped in the chuck, so I have something to indicate off.
Okay, last step is to drill and broach for the 5mm hex. There we go. I pre-drilled with the size of the hex across the flats. So this is a 5mm hex, and I drilled 5mm. I drilled a little bit deeper. I drilled 7mm deep. The hex will be broached 5mm deep. The rotary broaching is relatively simple if you have one of those things here. I did a video on building this out of a kit from Hemingway kits. This is a rotary broach. You can buy them commercially from Slater Tools, or Hoffman Group has one for very reasonable price, also very low profile. But this one is shop built. It has a ground 5mm hex punch in it that is hollow ground on the front. I do that on the lathe with a die grinder freehand. And the way this works is you pre-drill, then you bring this in contact with the part, turn on the lathe, add some cutting oil, or add some cutting oil now, and then you just shove it in. That's all the magic. Very, very fast process. Very, very reliable actually. Using a countersink. Clean it up. There we go. One nice hex. Last step is just to use a Cratex stick and just polish the face of the part a little bit. Oh, I forgot one step, which is not a problem. We can go back. In the bottom of the hole you can see the 6 chips formed by the hex punch. These get pushed down and collect at the bottom of the hole. In reality it wouldn't matter to leave them in there. They don't hurt anyone. But as we want to do a nice job, we will take the part back in the chuck and use the same 5mm drill as before to clean out those chips. The drill will weeble wobble around a little bit because bottom of the hole is very uneven due to the chips. There we go. Didn't hurt. Looks different right away. So we have the eccentric screw here done. And I also made this part here, which is just cylindrical with a screw hole and a thread on the end, and this bolts to the end of it. A flathead screw. And this grabs into the T-slot of the small mill this is going to be mounted on. And the way this goes together, so this goes in here, like this. The cam goes in here, and this piece with the flathead screw goes on here. Just like this. Now when we use a hex in here, you can see that this piece is moving in and out, and this will lock this blocked table of a mill. I have 2 gauge block stacks here. These are not my good gauge blocks. The table of the mill, the thickness of the table varies between 5.7 and 5.9mm. So I have to make sure that that this block clamps in every position of the table. And first stack of gauge block goes in. And this just simulates the thickness of the tabletop. And and it locks perfectly. Now for the other thickness, this is a thicker one. And it locks perfectly. I also added an M3 thread on the inside of the hex, so I can use a screw or a puller to get these cams out in an emergency. If something seizes up or breaks, you want to get them out in some way. And if it's flush with the surface and there is only a hex showing up, good luck. You could TIG weld something to it if you have to salvage it, but if you have already a thread in it, it's easier. Last step, this block was wire EDM cut. It was vertical and it was cut out of a disc of cast iron on a wire EDM, so it's basically an electric bandsaw. It uses a wire and electric current to walk around the contour and cut it. CNC machine, it can do parallel parts, but it can also do, by moving the upper wire guide off center, it can do weird shapes with conical contours or with completely different contours on the lower and upper side of the part. Maybe the part is square on bottom and round on top. The so-called squircle. Wire EDM is quite a cool technology, and in tool and die and mold making, irreplaceable at the moment. So this was wire cut. I ground the outside surfaces on a surface grinder because the owner didn't like the EDM finish, which looks a little bit rough. It isn't really rough. If you put a stone to it and you give it 2 or 3 strokes, it's almost like polished. But we decided on surface grinding it, and last step for me is to chamfer all the edges on the face. On the cross section, the chamfers were already cut with the wire EDM, so that's not a problem. But I already did all the chamfers on this side here. These are hand filed. Need to do the chamfering on the T-slot still, and then the other side needs also to be chamfered. And I get often questions about hand filing, so I will show you that. Moved my benchwise over. It has copper jaws, but with copper jaws you have to be careful. Steel particles, when you do, as I do a lot with working steel, will embed itself into the jaws, which happens because copper is soft. So if you clamp a finished part like this and you have a steel particle embedded in the jaw, you will get an imprint in your nicely finished part, and that's quite annoying to get rid of. Take a file, fine cut file, and just clean up the face of the jaws before you clamp a very expensive or very finely finished part. So for chamfering, for filing a chamfer, it makes sense to hold the part at a 45-degree angle, so you just have to hold the file flat. I like these Valorbe Habilis files. I'm using thick-walled shrink tube, heat shrink tube with glue lining as a handle on them. They fit nicely in the hand. This is a number 4 Swiss cut, so it's very fine. And we'll start by this long edge up here. And I don't go this direction. This will chatter. I'm going this direction. So I increase the length of engagement of the file on the edge.
Here we go. That's those two corners. This comes with experience. I eyeball the width of the chamfer. Now for the short edge here, close to the angled surface here. I will bring the camera in closer. A normal flat file has 3 sides that cut, the 2 large faces, one of the sides, and the other one is a safe edge. That's what we're going to use here. Place it here, up in the corner. You don't see anything. You place it here in the corner with the safe edge up against in it. But if you started to file like this now, you still would cut into this angled edge here. So what I do is I use 1 or 2 fingers to rest my file up against it, like this, as a filing guide. There we go. That's all that's to it. Same on this side. In this case, I will have my fingers on the other side of the file guided into the corner, which works also. There we go, that's the short edges. Now we want those sloped edges. Make sure the jaws are clean. Make sure the part is clean. Just blow it off with compressed air. And in this case again, safe edge up against my fingers. And you tilt the file a little bit and you feel when you get full contact with the edge. These long edges of the T-slots, those can be done with the full length of the file. If you look straight down a file, larger files usually have a belly on one side and are flat on the other side. These Valorbe files are straight as an arrow and parallel. So you drop it onto the part, keep it flat, you just work the edge until you get a chamfer over the whole length that looks like you want. And yes, you see me filing with the file dragging on the backstroke. Most people say, that's bad practice because you wear out the file. Guess what? Files wear out because they're a cutting tool. But you have way more control by doing a slight backstroke with dragging the file instead of pushing, lifting, trying to reorient the file, getting it back in contact. It's slower and more prone to error usually. Oh, another thing, if you put pressure in front of the file, you will put a bow into the part because you bent the file. If you want to do something like this, put pressure in the middle. That would, in theory, put a dent in the middle of the part, but your filing motion counteracts that because we're not perfect, and you end up with a pretty straight flat. That's also what you do when you want to file a flat surface, which nobody does anymore because we have mills and surface grinders. But for fitting and alignment purposes, this can be a useful skill. And I'm ranting on forever. Safe edge to the left, guiding it with my fingers, and by holding it at an angle, I can sneak into the T-slot and hit this edge here with full contact, and put a decent chamfer on it. Something else we will do is to round or ball over the edges. Corners, not edges. Take the file and you put a corner break on here that intersects with all the meeting chamfers. Just like this. Makes it way nicer to touch. And you can even round it over a little bit. Don't overdo it. Looks pretty decent now. Last step could be to take some fine emery cloth, rip it to the width of a file, and clean it up a little bit. Even a number 4 Swiss cut file is relatively coarse compared to, say, 400 grit emery cloth. Also, you might notice that I roll the file with the emery cloth a little bit over the edge of the chamfer. So I'm basically deburring the deburr. Filing, as most chip forming processes like milling or turning, filing will also create the secondary burr. That's what we take off here with the emery cloth. You can also use a Scotch-Brite wheel, but the finish on this part doesn't command for Scotch-Brite wheel finish. It would look quite horrendous. All done, all finished. I'm quite pleased with the finish I got on these parts. As you can see, it's not exactly mirror finish, but it's kind of reflective. Don't have any deep scars in it. Didn't drop it, which is also always good. I'm pleased. So that's the WW83 style watchmaker's headstock riser to mount the headstock on a 6-sis watchmaker's mill, and I will show you a picture of it now. On the left side you see the headstock of the small lathe put on this riser, sitting on a mill table with the mill spindle in horizontal position. The mill spindle is not original, that's an NSK high-speed spindle. That's quite a nifty setup, and this riser block will do a good job there. In the photo you see the riser block in its EDM cut finish.
Let's say you have a stack of thin plastic material, or sheet metal for that matter. Works also with sheet metal. And you want to mill them on the end nice and square and clean. Burr holding is always a problem with thin material. Vacuum chuck is nice, but you always can only do one, except for when the vacuum chuck is large enough, then you can nest the parts and do multiples in one setup. Or you glue them down with double stick tape and mill them. That's messy if you have to do more than one. I like to machine them as a stack. Just clamp them and side mill them to size. And the way I do that, I have a large parallel. This is a piece of hardened tool steel surface ground, clamped in the vise, just bottomed out, nice and even, with the fixed jaw of the vise exposed back here. So I have something to butt my parts up against, like this. Then you eyeball them to be aligned on the side you're going to cut. we're going to mill both sides. I will show you how to flip them over without losing registration against each other. Press them up against your hardened jaw back there. And take a parallel, put it on top. Vice grip, clamp it. I'm clamping onto the large parallel down here. Clamp it back here, and you're good to go. Now we can do our milling, and these vice grips hold good enough for milling, as long as we don't overdo it. 10mm 6 flute carbide end mill. Get rid of the little bit of burr we get. Check if we cleaned up. We have some spots down here that are not clean, so I will go back, take another 0.4mm, climb cut it, and that should clean it up. Gives a nice finish back here. Get the tool out of the way. First side cleaned up nice and good. Now we need to turn it around and mill the other side. But if we open these clamps now, we will lose our registration between our layers of material here in the X direction, and all will come out in a different length. So we take another pair of clamps, we go to the outer end of the material out here, and we clamp the stack together. Now we can open these two clamps, move the table, flip it 180, move it in, butt it up against the rear stop, and reclamp it with our parallel to spread out the loads. There we go. Now we can remove these clamps and mill the second side. It's as easy as can be. It's not a very complicated technique. A lot of people obviously know of this technique, but maybe it's handy for somebody new into machining. Ran the end mill along the other side, and now checking the dimension. Should be 205 millimeters. 205, very close to 0, so that's alright for PVC parts that get glued together. This technique has limitations. If the stack up gets too high, a layer shift is very likely to happen. These, especially plastic sheet material, is not very consistent on thickness. It has, if you look up the tolerances for plastic sheet, they're quite horrendous. And if you stack them up, they can shift and squirm when you clamp them down and move and whatnot. So keep that in mind. Do not mill a 200mm stack up of PVC material to length at once. The other thing, if you make an error with a stack up, all the parts are wasted, not only one. So keep that in mind too. In this case, worked out beautiful. The PVC comes with protective film on one side. When I do my stack up, on the first and the last layer, I have the protective film face the inside of the stack for a reason. When the end mill moves along, the spiral tends to pull a burr up. Burr is not a problem. You can scrape that off or remove it with one of those flexible abrasive Cratex blocks. But if you pull up the protective film, that's just annoying. So flip it over so the protective film is sandwiched in the stack and you will get a perfect clean cut. No problem with the protective film. Both sides. So yeah, that's technique for milling stacks of thin material. Get yourself a large piece, a large parallel. Even if you just buy a large piece of precision ground flat stock and mill the edges square. That's super useful, super helpful. You will use it all the time. Just to support fragile or flimsy pieces of material. I need to make a bunch of, or rough out a bunch of these U-shaped parts out of cast iron. They start as a flat piece like this one here, held in the vise, and I'm using a 6mm, roughly 1/4 inch, 3-flute carbide end mill to rough out the majority of the material. Depth of cut is 4mm, I'm running 1600 RPM and I'm feeding about 200mm per minute. And I wanted to show you something. Normally, common sense tells you shouldn't rough on a manual mill with Climbcut. But there are cases when you can, and it's very advantageous. First cut obviously will be a slotting cut, but after that we'll come back and talk about it. Okay, now we have the slot in, and normal wisdom would be to step over like this, and with the end mill going that direction, the part moving this direction, do a conventional cutting pass to rough out the majority of the material until you have full width. In this case, that's very dangerous. The part is held between the vise jaws and we remove the material that supports against the clamping pressure. We have some material left, about half the thickness of the part left here, but still the part will bend a little bit, which isn't too bad because we're grinding it afterwards anyway. But conventional cutting will pull the end mill this direction into the part, and in the same way it will pull the material in this direction towards the end mill. And that's a very violent cut. You hear a conventional cut right away. It's relatively loud compared to a Climbcut, and there is high probability that the part would get yanked out of the vise in this situation. If we go over here and we take a Climbcut, everything's great. The end mill gets pushed away from the material and the material gets pushed towards the jaw, so we do not create a dangerous situation here. The problem with climb cutting is, of course, you have the manual milling machine has an Acme lead screw and it has a little bit of backlash. Depending on the mill, it can be a lot. This mill has about 0.25mm of backlash. That's enough to wreak havoc, because when you go into climb cutting, the end mill wants to feed the part itself. It's self-feeding, and it takes a bigger and bigger bite, and then something will break. But if you go, that only happens if your side engagement is half your cutter diameter or less. Then this can happen. If you go beyond the center of rotation, this is 6mm end mill, and I will step over 5mm, and I will take a climb cut, nothing will happen. It will sound great, it will cut perfectly fine, and no danger at all. Let me show you. As you saw, very safe cut, very smooth running, went very fast for a manual mill. And I wouldn't dare to use a larger end mill in this case, like an 8 or 10 millimeter, maybe a roughing end mill, because as I said, the setup is not very robust. But for those few parts, only have to do 12 of these. That's fine. It's fast enough. And 6mm end mill removes, you can push it, it removes quite a bit of material and they are cheap. 6mm carbide end mill, 3-footer, is something like 10 to 15 bucks. And after 6mm, the prices go up dramatically if you buy a larger carbide end mill. So I usually buy maximum 10mm carbide end mills, but I try to stay 6mm and below. So we're coming to an end of this rather long Shoptalk episode. Thank you all for watching. You might check out John Saunders' channel, YouTube channel, NYCNC. He visited me here in my shop and he filmed a 1-hour tour of my shop, and you might enjoy seeing my shop and even myself from a different perspective. I will put a link down in the description. Thank you all for watching and see you next time.